extremely honoured to be here and very grateful to Professor Cooper for inviting me and looking after me so well. I must apologise for this room, which is appalling. I hope the hotel refund your money because you can't see from the back of the slides. So if anybody wants to move around, stand, get to a position where they can see the slides better, feel free. It might be a good thing. Can we lower the lights? I suspect your knowledge of Europe geography is as bad as my knowledge of Korean geography, so I thought it might be useful to show where I came from. This is Europe. This is the United Kingdom. This is Northern Ireland. This is Belfast. And that's my chemistry department. And there's my office. And this area from here, round here, is Quill within that building. I'm going to talk to you about the industrial applications of ionic liquids. You're all very brave trying to do all this in one morning. It only takes us 2 days to cover what you're trying to do in about 4 hours, so you have to concentrate very hard to follow all this, I think. I'm going to talk about industrial applications, and therefore I must talk about green chemistry. Now, I know everybody in this room, in fact everybody in Korea, is much more intelligent than President Bush, so I don't have to spend long on this. This is a photograph I took in China. Here is the factory. Here is the cloud of pollution being generated by that factory. Here we have it from a different angle. That is not green chemistry. Green chemistry is about doing things differently. It's also multidisciplinary and it's international. Here is a very beautiful city in China, Harbin, and just before the end of last year, there was an explosion in a petrochemical plant there. Because of that, the river was polluted. They had to close down the water supplies for 2 cities. And it also went into Russia and affected Russia too. So green chemistry isn't just of local interest, it's a global issue. And it's something we have to work together on. And it's the theme I'll return to. You can only do chemistry in the 21st century as part of a big team. One man and his dog working in a shed can no longer produce useful things. You have to work as teams with different disciplines, different nationalities, different centres if we're going to achieve anything useful. For example, I'm here, you are a Korean chemical engineering organisation. I'm not Korean and I know nothing about chemical engineering, so you are very brave listening to me. There is a measure of how dirty the chemical industry is. It's called the E factor. It was developed by Roger Sheldon. And the E factor is the ratio of the amount of byproduct produced to the amount of useful product in the process. Now, if you ask most people in the street, they will tell you the petrochemical industry is the dirtiest industry on the planet. In fact, it's the cleanest. It produces only 1/10 of a ton of waste for every ton of useful product. Whereas most people have the impression the pharmaceutical industry is very clean and very green, it's filthy. It produces between 25 and 100 tons of waste for every ton of useful product. And in 3 major processes, it produces 1,000 tons of waste for every ton of useful product. It's the most disgustingly evil industry that we have at the moment in the way it behaves. And if we want some measure of that, oil products sell at a couple of $100 a ton. Pharmaceuticals sell at $10 million a ton. It's not that they can't afford to do something about it, they choose not to. What are the problems with the chemical industry in the moment? To summarize it all in one slide, it's old, it's inefficient, there's a lot of solid waste, heavy metals are still being used and they shouldn't be, there's far too many process steps, and there's a lot of solvent waste. Now, I'm going to address in this talk the last issue here, as we don't have time to address the others, but with ionic liquids, we'll not just be addressing that, we will implicitly be affecting every other one of those as well. So we're looking for a global effect here, but the concentration will be on solvent. At the moment, and these are the best figures I could find, they're over 10 years old, I think they give an indication of what's going on. 2,300 million pounds of chemicals from the toxic release inventory were released into the environment. And of that, 70% went into the air, and these are volatile solvent contaminations. If we look at the way that breaks down by sector, then the evil man here is the chemicals industry. Most of this pollution is coming from the chemicals industry. So if you're an industrialist and sitting in the audience, hang your head in shame. There's only one good industrialist, and that's the ASF, who are working well. If we look at the UK and look at the way emissions have been affected by time, then we can see a major effect here from road transport sector, where we introduced catalytic converters and the emissions drop right down. If we looked at 2002 figures, the worst polluter, solvents again. So again and again we get the message, solvents are going to be bad for the environment, bad for green chemistry, bad for the whole of our lifestyle. So what can we do about it? We have 4 approaches. We don't want to use solvents. What's the best thing to do? Don't use solvents. Use solventless processes. And this is mostly carried out in the petrochemical industry by the use of zeolite cracking catalysts. Wonderfully useful where you're looking at very crude chemistry, breaking down a large molecule into lots of small molecules. Very difficult to apply to the pharmaceutical industry, where you're interested in adding maybe an 8th functional group to a molecule with 7 functional groups already. So, as we'll see, none of these are panaceas, none of these are cure-alls. It's actually a toolbox, and all of these have their particular application. The Greenpeace solution, use water as the solvent. This sounds great, because if you take water from the environment, put it back in, it sounds like it's very green. But if we went down to a river and took some water out of it, in Europe at least, the law stops us putting it back into the river because it's more polluted than we're allowed to put things back into the environment. So it's very expensive to run a process in water, but it's very expensive to clean up the water waste to such low levels of organic content you can release it back into the environment. Third approach, supercritical fluids, particularly supercritical CO2, genuinely green solvent now because we can take the CO2 out of the atmosphere. When we've finished, if it goes back in, the net balance is 0. It's a solvent with effectively an infinite vapor pressure, and therefore you can distill it around the system, move it about, no leaks. Negative side, not that many things are well soluble, and it's high pressure. Ionic liquids, we just had an excellent introduction. In fact, I could throw off my slides away after Professor Ku's introduction. Ionic liquids, effectively no vapor pressure, and therefore no VOCs. Advantages over supercritical fluids, many more things are soluble in them. Disadvantages, more expensive. We'll come to that. However, our job in Quill, if I get a chance at the end, I'll say what Quill is to feed information into this box, because this is the youngest area. This is what we know least about. So that an industrialist maybe sitting over here can decide whether or not he's going to use this, or this method if he wants to develop a green process. They're not in competition, they're there to support each other. There is no merit in somebody saying, I'm doing supercritical fluids, this is better than ionic liquids, this is better than... None of them are better or worse. They're all there, and we want to take advantage of the best that each category has got to offer. We group together supercritical fluids and ionic liquids under the heading of neoteric solvents. Why? Because we're largely ignorant about both of them, and this means that that term reflects that ignorance. Supercritical fluids, it's a new state of matter. We know a lot about the physics, we know much less about the chemistry of things dissolved in supercritical fluids. Ionic liquids, as the name suggests, they're liquids made of ions. We've had 2,000 years of chemistry in a molecular environment. We go back to ancient Rome, ancient Greece, ancient China. All the chemistry was done in water. It wasn't until we come to the 17th century that we start to work with other solvents like hexane or alcohol. We come to the 19th century, we use liquid HF, we use bromine trifluoride, we use liquid sulfuric acid, liquid ammonia, lots of new solvents, lots of new chemistry, every one of them molecular, every one of them following the same rules. We move to ionic liquids, 2 things have changed. The thermodynamics will be different because our energies are now largely Coulombic in nature. And the kinetics will be different because the solvation sheets are different. Well, if the thermodynamics is different, and if the kinetics is different, that's the same statement as the chemistry is different, because chemistry is purely a combination of thermodynamics and kinetics. So this tells us that we know absolutely nothing about what we're going to expect until we do the experiment, which makes it a lot of fun, because everything you do is new. And the students love working in this area for that reason. Now, can we show you what an ionic liquid is? I'll show you the oldest example we know of an ionic liquid. If I can, let's hope everything works here. Oops, that wasn't meant to happen. There's an ionic liquid. There's two of my students doing their PhD on dissolving things in ionic liquids. I haven't seen them for a while, they're little people with fairy feet. Their PhD was to see if gold dissolved in an ionic liquid. So they took their experimental equipment, gold ring, threw it into the lava, and magically it dissolved. So we've known since the time of Middle Earth that ionic liquids are good solvents. One slight problem, they're too hot. You take an organic compound, let's do this manually I think. We take an organic compound and put it into an ionic liquid, you will just convert it into carbon dioxide, it will just burn. So what we have to do is lower the temperature to room temperature. Now how we do that is a lecture in its own right. I'm not going to tell you, but we can talk about it later if you want to know. We've managed to bring temperatures down from several thousand degrees centigrade, in some cases to a melting point of -100. And we know how to do that, it's easy. So what do we now mean by an ionic liquid in the laboratory? They're salts. There are only ions present. An ionic liquid comprises only of ions. It is not the same as a solution of ions in water. This is not an ionic liquid. This is a salt solution. This is what we've known about in great detail since Unsaga and Bronsted, and all the work was done on aqueous electrolytes. By definition, for no good reason except for patent law, they are considered to be liquid, ionic liquids that they melt below about or approximately close to 100 degrees centigrade. It could have been 200, it could have been 150. It's arbitrary. There's no reason. But patent law seems to have settled on this number. And they've got no measurable vapor pressure at room temperature, but we'll come back to that later too. This is what they look like. They should be colourless or pale yellow. Unless you buy them from BASF, in which case they're black. But the colour doesn't matter. The colour is a part per billion impurity. It affects nothing in the chemistry, nothing in the engineering. The only thing it affects is if you want to monitor your reactions by electronic absorption spectroscopy or fluorescence, and then you need the colour gone. But for most practical purposes, although it's very nice, it's aesthetic to work with a colourless ionic liquid, for all practical purposes, the colour has no effect on the chemistry, the physics, or the chemical engineering. There are 5 key reviews. Now, there are much more recent ones than this, but I find it better to go back to the older reviews when people took less for granted and therefore explained things more. So the first one is a review for idiots, chief executive officers, politicians, heads of department, that sort of thing, that don't have time to do any chemistry anymore. This is a sort of introductory treatise. The best review is by Tom Welton. This was published in 1999. This is the car mechanics view of ionic liquids, how to use them, how to dry them, how to work with them, how to make them. By far the most useful review. This one is aimed at industry. This one concentrates on catalysis, and this one concentrates on enzymes and ionic liquids, which we just had an excellent introduction to. Key properties, they have liquid ranges typically of about 300 degrees centigrade. Water is only liquid for 100 degrees centigrade. Liquid ammonia is only liquid for 40 degrees centigrade. Ionic liquids over 300. If you recall that we can double the rate of a reaction for every 10 degrees change in temperature, then we have got from this huge kinetic control over any reaction we study. They will dissolve almost everything. They will dissolve coal, they will dissolve rocks, they will dissolve almost every known organic material. They will dissolve most inorganic materials and most polymers. What they don't dissolve is glass, stainless steel, polythene, and PTFE. Which only goes to prove God was a chemical engineer, because he said, have a universal solvent, but you also can have reaction vessels. We can have superacids here, more acidic than Euler's superacids. We can protonate benzene at room temperature, 20% C6H7+. Some of the ionic liquids are water sensitive, others are hydrophobic and air stable. Most are thermally stable up to 200 degrees centigrade. You can buy them. I'm sure the ASF will sell you some. Citri, you have a local producer here. And you can make them, which is what I would prefer. I always trust the ones I've made myself rather than the ones I buy in. They've got no measurable vapor pressure at room temperature. We'll come back to their flammability. They have a whole range of acidities. They make very concentrated solutions, and therefore they're ideal for process intensification. They're often catalysts as well as solvents. We see many examples of highly selective reactions, and green and exciting and interesting. There's a lot of new chemistry to be discovered. They've become known as designer solvents because there are 10 to the 18 of them. That is 1 trillion. The new paradigm in using ionic liquids is that because there are so many solvents, you can control the chemistry with the solvent rather than the traditional approach of try it in methanol, try it in methyl cyanide, try it in dichloromethane, try it in THF, and when you find a solvent that works, optimize it. Here, we use an intellectual approach. You design the solvent to give you exactly the properties you want to study. You want good product yield, you want high selectivity, you want your reagent soluble, you want your product insoluble. All of these things, because we have got so many ionic liquids, we can design it. And that is the difference of ionic liquid work to conventional solvent work. The control all comes from the solvent. We've talked about new chemistry, VOCs. These two are tied together. They need to be recyclable to be cost effective. This has got nothing to do with green chemistry, although it is green, it is pure economics. But then economics is part of green chemistry. I've had a lot of people come to me and say, we have a very green process, but nobody's interested because they say it's too expensive. They don't understand the word green, because green means you're going to use it, and if it's too expensive to use, it's not green. And many of these things we need to scale up, which is the key thing I want to talk to you about today. We can think of this then like an artist's palette. We have cations to choose from, we have anions to choose from. We pick, mix, match, and make what we want. And there's many. Even if we just take the imidazolium cation, we can change this chain length. We can go ethyl, butyl, hexyl, butyl. We can make that chain as long as we want to. The question is, do we want to? Is there any point? We think so. This is how we get the number. There isn't much time, I'll skip over that one. There's a question about ionic liquid volatility. We've said for a long time they're not volatile at room temperature, but that doesn't mean you can't distill them. And people have said to me, why do you say they're volatile when you can't boil them? Well, let's see. There is a boiling ionic liquid. It clearly has vapor pressure, but this is 300 degrees centigrade. At room temperature, even at 100 degrees, the vapor pressure is still undetectable. What this means is that we can have our cake and eat it. That when we want to work at moderate temperatures, there is no vapor pressure, no VOCs. But if for any reason we want to distill an ionic liquid, and purification is a very good reason, you'll see how beautifully colourless that was. You can take black ionic liquids, distill them, and make them colourless, if you want to. Why would you want to? To kill fluorescence is a good reason. So, you have the advantages and disadvantages at the same time, and that's a very good combination. We discovered this working in collaboration with a Portuguese group, and we were fortunate enough to get into Nature, and even more fortunate. I think it's the first time ever that ionic liquids have been on the cover of Nature. We hope this is going to happen more and more often from now on. Are they flammable? Well, it's a very good question. Conventionally, no. I'm going to see a movie taken in our labs. Here we have a phosphonium ionic liquid. Here we have an imidazolium ionic liquid. Here we have kerosene. The people at the back, this means nothing because you can't see this, I apologize. And here we have Martin Earle, who's a very persistent postdoc, and he wants to prove something, he really tries to prove it. He wanted to prove ionic liquids burn. So he took a butane flame, tried to burn them. Now, while you're watching this, think if you were on a factory and you were surrounded by either tanks containing ionic liquid or tanks containing toluene, where you'd rather be. Because these do not burn. You can try. Go back and try again. The one in the middle is kerosene. Very different. There is an intrinsic safety in using ionic liquids in an industrial situation. Absolutely intrinsic. However, that does not mean that they won't burn under any condition. If we now take a totally different experimental setup, this is information from the US Air Force. Let's see if we can make this happen. I'll run that again in a moment. There we go. Let's optimize this. I'll explain what we see. This is a hot nichrome wire, and this is an atomizer. So the ionic liquid now is being sprayed onto hot nichrome, rather like you take aluminium powder and put it into a Bunsen flame, it will catch fire. Well, so now we'll see if we take ionic liquids under the right conditions, and you watch what happens, it catches fire too. So flammability is a matter of the condition in which you're looking. Under conventional thermal situations, they don't burn. But if you atomize them, make them into a huge surface area, then they will burn. So every general statement you hear about ionic liquids, you must say to yourself, is that true in all situations? The answer to that question would usually be no. There are 10 to the 18 ionic liquids. Clearly, any statement is going to not work for some of them. Statistics tells us that. So does common sense. Do you have to work in a dry box? Well, you can, but it's very cramped. I mean, you can't move your arms, you can't pour things well. The reality is that only very few ionic liquids are water sensitive, and they're usually the ones based around chloride or around aluminium chloride. So if you're working with those, you still need the dry box. For many others, you need to work under nitrogen, because even though they might be water immiscible, even though they might be stable with water, they usually absorb water from the atmosphere. They're like a sponge. You put an ionic liquid on the bench, water just jumps into it. So it's advisable to work under dry nitrogen if you're working with ionic liquids. They are usually considered to be universally miscible, but in fact there are immiscible ionic liquids. Here we have a phosphonium chloride mixed with butyl methylamidazonium chloride. They don't mix, they form two layers. The blue is cobalt, just to make it clearer, because it's not easy to see the barrier between two colourless liquids. So there's a pair of immiscible ionic liquids. If we now add some other liquids, we can get four phases coexisting: pentane, phosphonium ionic liquid, water, methyl methylamidazonium ionic liquid. What are the implications of this? Here is copper dissolved in two ionic liquids, which are immiscible. Here is cobalt dissolved in two ionic liquids, which are immiscible. And here's a mixture of cobalt and copper. And the cobalt goes into the top phase, and the copper goes into the bottom phase. So you can use this for metal separation, or any other separation process where you've got a differential solubility of your substrate in the two different ionic liquids. Are they toxic? This I'm going to skip over. We just had a very, very good presentation about that. But I will point out that there's going to be a very important meeting in Berlin next year. It's going to be 4 days. The first day will be a workshop on ionic liquids, teaching the basics. The second day will be a workshop on toxicity and biodegradability, teaching the basics. The third day will be original papers. And the fourth day will be to develop a global strategy for designing ionic liquids which are both non-toxic and biodegradable, which is where the future has to be. We cannot go and carry on working with ionic liquids which are considered to be toxic or non-biodegradable. We have to develop methodologies to be able to ensure that they're both. Are they green? No. Never believe anybody that tells you ionic liquids are green. When you see a paper starting off with this statement, stop reading it, throw it in the dustbin. It's not worth it, they don't understand what they're doing. There are some green ionic liquids. and there are many non-green. We could design them. We could make paraquat cyanide. What evil liquid that would be. But it's still an ionic liquid, and it's clearly not green. Most ionic liquids are not green. You can design them to be green. We can take them from the car pool. We can take them from amino acids. We can make them from materials we know to be safe. But that's part of what that workshop is going to be about, how to do that. But do not treat seriously any statement that says ionic liquids are green. They're generically not true. We've heard about polarity already. In Quill, which is a consortium of industrial firms, we've published a map for industrial innovation. What that means is it's showing you how to move from ionic liquid chemistry on the bench to ionic liquid chemistry in industry. It's free for download on our website. Just set Quill into Google, go to the site and download the document. Here's one figure from it, and this is talking now about the applications of ionic liquids in unconventional ways. We tend to think of them as solvents for chemistry, solvents for biocatalysis, solvents for catalysis. Here are some of the things you can do with them with nothing to do with their properties as a solvent. Heat transfer fluids, refractive index matching, lubricants, fuel cells, jet propulsion, paints, drug delivery. All of these things are possible using their material properties rather than their solvent properties. We don't hear so much about this. This is where I think we're going to see many new industrial processes arising, making use of that. Can they be made on an industrial scale? Yes, you will hear more about this in the last lecture today, I think. This is the BASF plant in Germany for making methylamidazole, which is one of the key starting materials for making the most popular of the ionic liquids. I don't have to give you details. You can see from the size of the plant that we're talking industrial scale. Can ionic liquids be industrialized? The fact there are now over 4 suppliers that will produce over 50 tons of ionic liquids tells you that yes. In fact, that is the first industrial process, making ionic liquids. You go to Merck, you go to BASF, DuPont are now making ionic liquids. All of these firms will sell to you Cytec, Sekem on a 50-ton scale. That is so important. Industrialization doesn't happen if you only have one supplier. You have to have competition, you have to have alternate suppliers. We now have those. And the first firm to really show to the public that the ionic liquids can be used industrially is BASF. The Basel process was the first publicly announced process using ionic liquids. And it was a real breakthrough. This says over 1 year. This is an old slide. It should say now. Coming on for 3 years now, I think it's been running. Certainly over 2 years. The chemistry is, I know you're chemical engineers, so I've kept the chemistry simple. It doesn't get any simpler than this. You react the phosphorus-chlorine bond with alcohol, you make a phosphorus alkoxy bond and release HCl. In the traditional process, the one that's been running for many years before, trimethylamine or triethylamine was used as the base to absorb the HCl. In the Basel innovation, they used methylamidazole. This is the team that developed it. This is Matthias Mars, who's a very, very clever chemist. It took them 3 years from the first experiment to it being working on an industrial scale. The normal time is 15 years for a process to go from the lab to industrialization. So ionic liquids are not only extremely useful, they shortcut the time from the first experiment to the industrial process. Why? Because it's just a solvent. And we know how to work with solvents. They just happen to be solvents which are ionic. And the technology is very similar. I'll show you a BASF movie which they've given me permission to show. First thing you're going to see is the original process. Now, this was not directed by Quentin Tarantino. There's not much action. There's not much tension. Nobody dies. No blood. Sorry, I know Korean movies are full of blood, but no blood here. And what we're going to see in very excruciatingly slow detail is 3 liquids being added to a flask. This is the reactor, and they fill their reactors very full of BASF. Here's the top of it. This is the phosphine going in. Dramatic addition of the drops. And now we're going to see the problem with the conventional process. I'm going to jump forward in time. And that's the final state. Triethyl or trimethyl ammonium chloride is a solid. And from this you have to separate your product. Now, it had been Tarantino, this would have been red and they could have sold it as tomato ketchup, but that is a chemical engineer's nightmare. So what Matthias Mars did, in a very clever idea, instead of using triethylamine, he used the 1-methylamidazole. His product, therefore, wasn't a solid, it was an ionic liquid. And now what we're going to see, see the top of the reaction here? In real time in a moment, we're going to see, there's the reaction complete. And this is now the real-time separation of the product from the reactants and from the solvent. The upper phase is the product. The lower phase, which you see separating out in real time here, is the ionic liquid, the other product of the reaction. That separates faster than they can get the mixture out of the bottle of the other. And then in less than 2 minutes, there is your product. And there is your ionic liquid. And here is the chemical engineer's ideal separation. Open a tap and separate. Let gravity do the work. And that is it. Now, I'm going to ask the audience a question in a moment. Okay, you're all chemical engineers. How much what factor do you have to increase your space-time yield by to change your process? To come up with new plans? What number? Let's have some answers. Factor of 10, would that do it? Your space-time yield that went by 10, would you change your plan? Silence. You are chemical engineers, right? I mean, my first year undergraduate was a mental this. Professor Koo, how much do you want to see?
I'm waiting for your answer.
You're a room full of cowards. Would you change it for a factor of 100? If you went up by a factor of 100, would you change the process? BASF, it went up by 80,000. Space-time yield went up by 80,000. The economics speak for themselves. You get rid of your old plant and you build a new plant. And that's exactly what they did. And they've had the first successful process with ionic liquid running for a long time. Here's the comparison. Look at the way that space-time yield changed. The yield doubled. And instead of creating waste, you recycle the ionic liquid. It's an ideal green process. And because of that, they won the European Chemical News Innovation Award, because it was green. Even though there were bigger processes in competition, they won. And here's the citation for that award, not just because the chemistry was good, because they were impressed by the way BASF had realized it could take the innovation further and create a licensing opportunity with the technology. Any acid-based neutralization could in principle now use the Basel process. They've also been busy. There's a pilot plant where they're looking at breaking azeotropes with ionic liquids. There's a patent out on this, as you might expect. This red line is the conventional THF water azeotrope. There's the azeotropic point. There's the theoretical line. You add an ionic liquid, and you can just distill THF away from the water, completely break the azeotrope. You can also use ionic liquids to stop you having to use phosgene. You can use HCl instead. And here we get the current process, the diol going to a dichlorobutane using phosgene. If you use HCl, you get a horrible product distribution and almost nothing of what you want. You take the HCl into an ionic liquid, and you get well over 95% of the desired product. Here we change the chemistry, as we said before. Here's an even more dramatic example of changing the chemistry. You take the reaction of toluene with nitric acid, you carry it out in a halo ionic liquid, and you get 99% plus of halotoluene. You carry it out, the same reaction, in a triflate ionic liquid, you get 99% plus of nitrotoluene. And you carry it out in a mesylate, and you get 99% plus of benzoic acid. You change the chemistry by changing the solvent, as we said earlier on. And there's no example I know of in conventional solvent chemistry where you can see those effects by solvents. Now, although the ASF were the fastest to announce they were doing it, Eastman Chemicals has been doing it for at least 6 years before, but keeping quiet about it under industrial secrecy. This is the Eastman Chemical process. They are using an ionic liquid here to make 2,5-dihydrofuran. They had a plant operating for 8 years, since 1996, making 1,400 tons per year of product. They closed the plant down at the end of last year, not because it wasn't working well, but because the market had dropped for the product. So that's two major processes. IFP have a process for license for the alkylation of butene to isobutane. Better dimer selectivity than the current process. Reactor size is much smaller. The cost of running it is reduced by 50%. I haven't time to dwell on this. What I really want to show you is ionic liquids chemistry that really entered the real world now, because last year Yves Chauvin won the Nobel Prize. He used 22 slides in his lecture, and 2 of them were about ionic liquids. Here is his introduction to ionic liquids, and here the process I'm just describing to you, the dimesol difosol process. You know something is happening when Nobel Prize winners start to talk about it. Degussa are using ionic liquids now, and this is pilot plant again, for looking at the production of siloxanes. This is not a good slide. These are Degussa slides. They're not good at slides. These are the starter materials, the silicon hydrides. These are the alkenes. These are the catalysts. I guess anybody at the back can't see below this level. This is an ionic catalyst, and this is a molecular catalyst. And these are the 3 ionic liquids which they used. Now, what do their results look like? They really can't do slides at Degussa. They really need to get a new presentation manager. But the conversions are all, with one exception, over 99%. Less than 1 ppm metal leaching means it's not leaching effectively. If we present those results differently and group them according to whether the catalyst is ionic or molecular, you find something we've known in Quill for a long time. You get the best catalysis when your catalyst is ionic. If you want to run a catalytic process in an ionic liquid, use an ionic catalyst. Here's why. The yields in either case are superb, better than 99%. Where the catalyst is ionic, we can increase its concentration from 20 ppm to 1,000 ppm. We see no leaching. Ionic liquids hold on to ionic materials like glue. They're better mounted than any catalyst is on a metal oxide or a polymer. You can't get them out again. But when you use a molecular catalyst, as you increase the amount of catalyst, you increase the amount of metal leaching, because that's not bound in the same way. So as a design feature, if you're looking for catalytic chemistry, use ionic catalysts. Degussa also bought part of a small firm, Solvent Innovations, that makes ionic liquids, and they're using them in paints. Ionic liquids are being used as paint additives commercially now. Now that might sound bizarre, because you'd think the last thing you wanted to add to a paint was a solvent which didn't dissolve. But they're not using it as a solvent, they're using it as a finishing additive. If you go to the website, you'll see they're selling it under the wonderfully catchy title of Tego Despair 662C. Just rolls off the tongue now, doesn't it? But this is being added to paints which are currently being sold. It makes the finish of the paint better. They have a better colour, they're tougher, and they don't fade so easily. So these are now commercially available. So ionic liquids could well be on the outside of your house when it's painted next. Air products have also been very innovative. They are now adding ionic liquids to cylinders of gases such as phosphine and arsine and BF3. The gas dissolves in the ionic liquid. You can get the same amount of gas in the same size cylinder now with an ionic liquid added to it and not have a pressure greater than that. So this is a huge safety feature. Their products are now selling, this is their website, what they're calling gas guard. The cylinders have the same amount of gas in as a conventional cylinder, but the pressure is below 1 atmosphere. Safety is huge. Again, it's a very green process. They won the Gassy Award. I don't think I'd advertise that if I was them. Ionic are using ionic liquids for cleaning purposes. This is for cleaning nozzles. We don't have time to spend much time on this, but this shows it very graphically. That was the old process, cleaning nozzles, and that's an ionic liquid process. Clearly, visibly, a better process. Japanese firm, Central Glass, have now industrialized the Sonogashira reaction, which is the reaction of an iodoarine with acetylene to make a coupled acetylene product. I don't want to spend time on the organic chemistry because you really aren't going to appreciate that. But this you can see very clearly that if you take the reaction in an ionic liquid, it's far better than taking it in a conventional solvent. The yields they were getting were up to 100% isolated, but on the practical case that would be difficult. And by a bit of clever chemical engineering, they were able to get very high conversions by running it for about 5 or 6 hours, and they've now gone over to this as the process of manufacture at Central Glass. Sasol, from South Africa, produce alkenes by the Fischer-Tropsch process. They are the most important alkene producer we have. But they produce more alkenes than there's a market for. Some of them have got the wrong chain length. They want to convert them into products which have got a better market. An obvious way of this is doing metathesis. Again, we refer back to last year's Nobel Prize on metathesis. They're looking now at the Grubbs catalyst in ionic liquids. Now, you'd think there wasn't much we can add to Grubbs chemistry. The Nobel Prize has just been given for it, so can we improve on it? Well, if you use the traditional Grubbs catalyst, no. 2 years of work said it was rubbish. Hopeless in ionic liquid. But if we go to the second and third generation Grubbs catalysts, the situation is different. The red line is the neat reagents. The blue line is the reaction in toluene, and the green line is the reaction in an ionic liquid. You get 20% greater yield in the ionic liquid than you do in conventional solvents. This is the selectivity graph for the same reaction. Look at that selectivity in the ionic liquid. In the other solvents, you not only don't get as good a selectivity, but it drops away with time. And if we move to the third generation ionic liquids, you can see we can get over 90% in terms of yield and better than 96% selectivity in ionic liquid. Far superior to any conventional solvent for the metathetic reaction. And if you see the effective chain length, ethyl, butyl, and octyl, fortuitously, and often is the case, the shorter chain lengths are the best. This is good because it's cheaper, because it's easier, and also because the longer chain lengths are more likely to be toxic, as we heard in the previous talk. ExxonMobil have got patents out on ionic liquids for hydroformylation, ionic liquids for formation of aldehydes from CO and arenes, and for the electrochemical oxidation of sulfur in naphtha. So again, a lot of broad applications being looked at there by Exxon. Eli Lilly have just published the results of a pilot plant study using ionic liquids to convert a methyl ether into a phenol. Very difficult reaction to get high yield on conventionally. Here we see the results of changing the amount of ionic liquid, and here changing the temperature. And in the optimized situation, they can convert 22 tons in an hour. That is an amazing result. Publications are going up exponentially. This is a slightly old graph, but the rise is steeper than the exponential curve. Last year, over 1,000 papers were published on ionic liquids. 10 years ago, 20. It's a dramatic alteration. The fact that Quill was formed here, we believe, has some impact upon the rate of publication. And here's the curve. The red curve is the experimental points, the blue curve is the exponential curve. Ionic liquid patents, a lot coming out, mostly from Europe and the USA, few from Japan, China. You're stuck in the others somewhere, I think. There's so many ionic liquid papers coming out that the people that do Citations Index have created its own website. Well, let's spend a bit of time on that. Here are the statistics. Look. 3,342 authors, 57 countries, 290 journals, and 745 institutions are published on ionic liquid. 10 years ago, it would have been 20 authors, 3 countries, 5 journals, 2 or 3 institutions. It shows you how much it's changing. If you're going to do something with ionic liquid, now is the time to do it before it's too late. And clearly, every country needs to be working here because of the huge industrial advantages which have got to be gained. Academia and industry has to work together. Academia and academia has to work together. Chemical engineers have to work with chemists, have to work with biochemists, have to work with theoreticians. Even, pardon me while I choke, even lawyers you have to work with. But if you don't, you'll achieve nothing. You cannot do it with just a couple of people. It is an international subject, it's interdisciplinary, and it's complex. And you need teams with every expertise to actually achieve something. If we look at the papers from 2003 and break them down into topics, you'll see, as you might expect, the most popular was synthesis and catalysis. How long have I got to go? Okay, you didn't give me the 5-minute warning. I'll skip over this, but just make the point. Very few papers at the moment on materials properties, lots on catalysis and synthesis. Obviously, these are the exciting new areas that are going to develop. In that same year, there were 33 papers on the Heck reaction, 12 on Friedel-Crafts, 12 on Diels-Alder. We don't need that many papers on these subjects. What we need is new, exciting things. They've been used for conserving biological tissues, for preserving corpses. That might sound an odd use, but if you think about the world consumption of formalin, which is a nasty smelling or evil liquid, definitely not green. We could replace those with ionic liquids. That would make place a lot healthier to work in. NASA are looking at them for jets on global positioning satellites and also for, believe it or not, intergalactic travel. I'll finish up by saying just a little bit about QUIL itself. It's an acronym. It stands for the Queen's University Ionic Liquid Laboratories. We have 16 firms who are a member. Firms I'm sure you know, like BP, ICI, DuPont, Merck, Sasol, Chevron, Seiken, Procter & Gamble, Novartis, Shell, all big companies. They each pay $30,000 a year to join. That then gives us a lot of money to spend on research, but the industries decide what projects we work on. All our projects are industrially directed, and the patents are shared by the members. They don't come to the university, they're shared by the members. Normal academic secrecy, you just go around and say, shh, we're not going to talk about this, but this is industrial secrecy. They take you to where it's -20 and gag you. These are the conditions we work under in QUIL. So when I talk to you about the chemistry we do, it's usually 3 years old because we're still waiting for the patents to come out. We are what is known as a Marie Curie Centre. What that means is that anybody doing a PhD in Europe, the EC will pay for them to spend time in Belfast and learn about ionic liquids. With Merck, we won an award from the Royal Society of Chemistry for what they call teamwork and innovation. We also, believe it or not, were part of the team which won the Presidential Green Chemistry Award from President Bush. Given my opinion of him, I'm amazed he ever gave us an award. And we were very honoured to receive from the Queen of England, an award which is called the Queen's Anniversary Prize. This is like an OBE, only it is for an organisation rather than for a person. And in February this year, my Vice-Chancellor, some ugly chap here, the Queen, the Duke of Edinburgh, received an award for ionic liquids. They have arrived. This is our team. This is a mixture of the industrialists who support us, and the academics. And let me make some really important points here. Sri Lanka, Netherlands, English, Polish, Russian, Zimbabwe. We have Australians, we have New Zealand, we have people from South America. We have 35 people, these are actually the researchers themselves who just take that. 35 people, 18 nationalities, and they include chemical engineers, physical chemists, organic chemists, inorganic chemists, analytical chemists, computational chemists, biochemists, all working together. But each person, whether they're a PhD student or whether they're a postdoc, has a team of 6 people working with them. So they lead a project, but they have support from all the other disciplines. So they don't work alone in the group, they work as teams in the group. And then this team works with 16 other teams in industry and 20 other teams in universities. That way you can do something useful. You cannot do useful green chemistry working by yourself. I can't repeat that message often enough. It's not green because it will never be used. And that's the end. Thank you very much indeed.